Okay, good evening, everyone. Last Monday, we looked through measuring performance of models, and we took it all the way through with a bit of hands-on. We looked at the different ways that you can measure performance. And then we also looked at um, the sklearn libraries or classes which are available. So being able to measure performance of models becomes very important when you are training models. But there's something else that becomes very important when you're training models. It's not just about being able to measure their performance. After you have measured and you have found the metric for performance, whether it is accuracy, whether it is precision or recall, whether it is F1 score, R squared score, whether it's a mean square error, mean absolute error, root mean square error, and all of that. What what do you do with that information? That is the next thing. Yes, while training models, that information, of course, is what is used to guide training itself. The loss is what you use when training so that your model can follow the gradient descent and move towards the local minimum, or well, the the absolute minimum or the global minimum. So you want it to get to the best it can get. So during training, the loss guides training via the gradient. But when you're done with training, and then you have now finished and you're measuring the model's performance, what you know, what are the things that matter? Why does it matter? Okay. Last time I talked about stopping training. So I'll just touch on that a little bit before we go on. There are three main things, right, that will benefit from your ability to evaluate a model. The first one is stopping training, which is what we are going to look at. The second thing is going to be um, selection of the best models for a particular problem. And then the third one will be selection of the best hyperparameters for a particular model or a particular architecture. But beyond that, we are also going to look at the bias and variance trade-off at the end of today. So, one thing that you'll find is that when you are training a model, it gets to some point, especially if the amount of data you have is very small, the model is very large, there will be a tendency for what we call overfitting. Overfitting is a situation where the model has so much capacity or you have so little data that the model begins to effectively learn the noise and the specifics in that data rather than learning general patterns. And because it is not learning general patterns, when it gets test data, it is not able to properly, um, it's not able to properly generalize. It won't get a good accuracy or a good score. It will not get it right, basically, on new data, on test data. And that's the reason why we test. So, we're going to talk about that and how to detect overfitting. But typically, the idea is if you are training a model and at some point the training loss continues dropping, the training loss is expected to continue dropping because you are training the model on the data. It's getting better and better at predicting that data as you are training it more and more. Your cycles increase. But you also expect that the validation loss should also continue to drop. So what is a validation loss in this case? So remember, training loss, you calculate it by calculating the loss on the training data. Validation loss, you calculate the loss based on the test data or validation data set. We're going to talk about the difference between validation data set and test data set. Typically, when you are training, if you are training a model, you take your data and you split it into two sets. You split it into training, test, and validation. The validation is actually the data set that you use to check if the model is overfitting or not. The test data set is a totally different data set that you keep aside. After you are done training, you use the test data set to evaluate the model. So that is the thing that we need to understand. Even though in some places there is a mix up in the nomenclature, sometimes you use the terminology test data set for evaluating the model while you are training it, right? But the test data set is actually used to validate the model or to evaluate the model after you have finished training. So when you calculate the loss on that, that's called the test loss. The validation loss is what you use when you are training models or when you are selecting between multiple model architectures, right? So typically what you would do is train a model on one, and then um, you would then validate, right? And then train another one. Okay, so that's typically what you do. Okay, so um, so if you are training a model and your training loss keeps going down, which normally should, if your training loss doesn't go down while you're training a model, that means the model is too small for that data. You can't use a linear model to be able to predict a you know a non-linear decision boundary, for example, or to model a non-linear decision boundary. So in that case, no matter how much you train, the loss will basically flatten out at a point and it will be insufficient. But normally, if your model is adequate for the data, then the training loss will keep dropping as you continue to train the model. But the interesting thing is that as you do that, if you're also checking the validation loss, which you should be, then you get to some point where the validation begins to go up. Instead of dropping, it starts coming up. At that point, it means the model is overfitting because the model is getting good at the training data, but it's getting worse at the data that is not part of its training data, right? But it's still part of that data set. So you don't want that kind of situation. So at that point, you want to stop training. But the only thing to do at that point is stop training. There's nothing else you would do, right? That model is overfitting effectively. So that's one of the reasons why you would stop training. Your model is essentially memorizing the training set from that point on. And if you give it new data that is not in the training set, its accuracy, its performance will get worse instead of getting better. The second reason why you want to stop training is computational cost or time constraint or diminishing returns after many epochs. So basically, computational cost is saying, well, you it's costing you some computational, but typical computational cost will come into play when the model is not really learning anymore. Or you've gotten to a certain point and you feel, okay, this is good enough for me, right? Even though the model can train and do better, but it's not worth the cost for me to continue training, right? So I'll just stop at that point and then take the model into production or to use. Then time constraints, the same thing, kind of a similar argument. Time constraint basically means you don't have any more time, right? So resources can be both cost and time. You don't have any more time. You have to deliver this model and deploy it. So there's nothing, the model could be better, but as it is now, it's good enough to use and we don't have any more time to wait. So you take it off of training, stop training, and you put it into production. Then diminishing returns is if essentially at this point the model is not really learning, or even if it is learning, but it's kind of the same as computational cost. What it's costing me is more than the extra benefit that I get from that extra maybe extra 5 or 6% that the model is accuracy or evaluation score that the model will achieve. So at that point, you can stop training. The third reason of stopping training is, of course, convergence. That's like the best reason, right? Convergence means your model has achieved the accuracy or the metric or the evaluation score that you want it to. Basically, it has gotten to, or it has even gotten 100%. That means it is able to predict very well. The gradients become very small, and they are so small. The difference in between this gradient and the next one, or the loss and the next one, is very small. In orders of thousands or hundreds of thousands. That is 1/1000 or 1/100,000 and so on. So, and then the training point has basically gotten to a minimum. That is the loss. At that point, there's nothing more for the model to learn. So you stop training. So those are some of the things that you look at when you want to, when you're training a model. You don't just stop a training of a model based on, oh, I picked 3,000 epochs. No. So this is one thing I want to let everyone here understand that in the real world, when you're training a model, you're training a model based on the business need. So don't just say, hey, just arbitrarily guess 50 epochs, 100, 3,000, 1,000,000. Yeah, that's okay. I'll train the model for that. No, you will not really get a good model. The idea is for you to train the model to meet the need. And the need can differ, like we have seen here. The need could also be train it until it's perfect. The need could also be train it until we can at least use it, until it's usable, right? But the need could be train a model, but I need it by Friday. Okay. So these are all the factors that would affect or determine when you stop training. So this is kind of a summary of it. If the validation loss is rising, it's overfitting. If the training and validation curves are diverging, it's overfitting. Same thing. If you have a plateau of accuracy or loss, that means the model has basically converged and it's not going to, well, it has either converged, right? Or it has plateaued, it has flattened out. It's not going to get any better, right? Um, yeah. So if the gradient norm is close to zero, that means the gradients are also very small. So again, the parameter will not update that much. And then if the learning rate is too small, well, this is typically in a case where you were doing an adaptive learning rate or a scheduled learning rate or a cyclic learning rate kind of thing. So you get to a point where it's too small. Of course, you could raise the learning rate and the models are learning faster. But then remember, some models, when you increase the learning rate, you actually destroy the information in the model. Because when you increase the learning rate, remember, it's the learning rate that determines how much of the gradient is used or what proportion of gradient is used to update the parameters. So if your learning rate is too high, that means the parameters will get massively adjusted, and that adjustment would be very bad. It could actually destroy the model or destroy the knowledge you've already trained into the model. Okay. So all of that is what we call early stopping. Early stopping is basically monitor validation loss during training. If it fails to improve for n epochs, so n epochs is what we call patience. You're saying, I'm going to wait for this number of epochs. If the validation loss fails to improve, or yeah, if it stays the same or starts rising, then stop training. Okay. And going forward, we'll be doing this early stopping as part of our training algorithm. And we'll also be looking at validation loss as well as training loss. So we'll be plotting those plots so that we can see how our models are doing, especially considering that we're going to start doing more difficult kind of training here. So typically the way you implement that logic is you train one epoch, you compute the validation loss. So remember, a validation loss is computed from the validation data. You just calculate the loss of the validation data. That's the data that you kept aside. You're not using it to train your model. Okay. If the loss improves, then you save the model. If not, you increment the counter. So the important thing and interesting thing here is you actually save the model at the best validation loss. So that later on, if the validation loss begins to deteriorate, you can revert back or restore that model and use it as the actual model that you keep. That's why there is what we call checkpointing. You store after every epoch, you should store, or after every X number of epochs, you should store your model. a copy of it somewhere that you have trained. In case something destroys that model, you can go back to the best model that you have. And if you are implementing early stopping, then that algorithm ensures that you are actually saving the weights of your best model at every point in time. So, yeah, if the loss improves, you save the model. Even though you increment the patience counter, that counter is a patience counter that you use to count how many epochs you should wait before you stop training, before the early stop. So once that counter is higher than the value of patience, which is the number of epochs you had previously specified, that you allow training to continue. Um, without any improvement beyond which you stop the training. And at that point, you stop the training. Okay. And typically, when you stop the training at that point, you always go back to the best training, the best model version which you had saved at step 3. So typically, the parameters you monitor if you are doing early stopping would be the validation loss, but sometimes you can monitor other parameters like the accuracy. You can calculate the accuracy at each point. You can calculate the F1 score, which if you can remember, F1 is the harmonic mean of the precision and the recall. So you calculate that as well. Then the other parameter is, of course, the patience, which is number of epochs that you wait before stopping early. And then you have the mode, which is if you're using mean, that means you are using loss, right? You are calculating based on loss, or max, you are calculating based on accuracy. So this is when you are implementing early stopping from sklearn, where you have to specify whatever parameter it is that you have passed in for it to monitor. So the advantages of using early stopping, it prevents overfitting, like we have seen. It saves GPU and CPU time. So it saves compute. You're not spending a lot of your compute and your time trying to train a model that's not going to get any better, right? And it also gives the best performing model automatically. Then the cons of early stopping is that sometimes if you don't select your parameters very well, especially the patience parameter, you may end up stopping too early when maybe the model gets stuck in what we call a local minima or a local minimum rather. So if you're in a local minimum, it means that you're at a point where the model is not improving, but that's not the best the model could ever be. And maybe if you continue training a bit, maybe it could find its way out of that local minimum, right? But sometimes it may not be able to get out of the local minimum. So a way to do that is to introduce some noise into your training that may allow it to escape that local minimum. So that's the thing. Then the other thing is if your validation metrics are noisy, then early stopping can be very sensitive to that, especially if you have validation metrics that are going down, right? And then going up, bouncing around. So it may delay the early stopping may not actually work because your validation metrics are just jumping all over the place, especially if the change is very small, right? The change in gradient, the change in loss is very small. So there are other methods that you can use when you are looking at early stopping. You can use a maximum epochs, which is what we have been using mostly for most people. It's a simple thing. You just specify, oh, do for 1,000 epochs. And once it gets to that 1,000 epochs, right, it stops. So the benefit of this is that it will prevent an overly long run. But the downside of the maximum epochs is that you can never be sure that your model has trained to its best, state, unless you choose a very high value of epochs, right? The other thing is you can monitor how your gradient is changing, how your losses are dropping. If your losses have not stabilized or flattened out, then you may consider that, okay, the epochs are too few and we need to increase it. And for some of you in your task, I think that is what happened. A lot of people just chose small number of epochs and they trained and that was it. So remember what I said, you're not just writing code. Machine learning is not about writing code. Machine learning is about training models. and thereafter deploying those models. So when you are training a model, the most important outcome you want is that your model has converged and has learned and has a very high accuracy, or the best in any of the scores. So that's the first. Then early stopping, like we've talked about, right? That one you use validation loss or metric or any other validation metric. For example, validation accuracy, validation F1 score, validation R squared score, or any of those validation scores. Basically, it's that those scores apply on validation data, right? And you find that in most cases, early stopping is the most effective stopping rule. So you see that sometimes you combine the two, you combine maximum epochs, but you give the epochs a very high value. Because if you just did early stopping without epochs, that means it's a while loop that doesn't ever stop. And that can be bad, especially if you have situations that don't allow convergence or your metrics are not stable, like we just said. So in most cases, you may actually combine maximum epochs with early stopping. As a matter of fact, you may actually combine any of these number of different stopping methods or all of them. The third one is the plateau-based stopping, where you stop when the improvement is less than a particular threshold for a k number of epochs. So what this means basically is you can specify a number. That number is a band that says if the improvement is not up to 0.0001% or 0.0001 loss value for 5 epochs or for 10 epochs, then I stop because that basically means that the model has flattened out. And the reason why I use a band instead of a specific value is that the improvement may never be an exact value. So you calculate the difference between the loss in the current epoch from the loss of the previous epoch. That's the increase in loss, or that's the improvement in loss. And if that improvement is not up to this value, then we stop. So that's one. Then accuracy, see, accuracy is an order of magnitude higher. Basically, what we're using for accuracy improvement is 10 times higher than what we use for loss improvement. That's to show you that loss is typically a very small value. It's a decimal fraction and it's just expressed as such, while accuracy is typically expressed as a percentage. But even if you're expressing accuracy as a fraction, its value is typically higher than the loss. So that's a plateau-based stopping. Then we also have another option where if you are on a plateau, you don't just stop immediately, you reduce the learning rate. So this is a strategy that is used on a lot of large systems, deep models like the deep neural networks, mainly because of the nature of the loss landscape. We're going to talk about loss landscapes when we talk about optimization later on. But because of the nature of the loss landscape, you find that sometimes the model doesn't get any better because your learning rate is too high. So what you do is you reduce the learning rate by a factor of 10. So if the learning rate before you started was at 0.1, you can reduce it by 10 to 0.01. And after training it for some time, reduce it by 10 again to 0.001. So what happens in that case is that you are expecting that because you have gone to a narrow part of the loss landscape, right? If you go on a smaller learning rate, the model can actually still learn a bit more, okay, and keep going until it gets to a minimum, right? So that's the principle behind that. Um, so that's what we call a learning rate schedule. But sometimes you may not use a learning rate schedule. Learning rate schedule is actually where you specify learning rates based on a particular schedule. But this one is based on plateauing, on performance, right? On the metrics that you measure. So if you have reduced learning rates up to a very low value and the model is still not learning, or maybe has learned, but again, it plateaus again and doesn't learn anymore, then that's time to stop. Okay, so that's the learning rate, reducing learning rate on plateau. Then we have gradient-based stopping. Gradient-based stopping is when the value of gradient becomes very small. So again, remember the size is a gradient that determines the amount of um, updates that will be added or subtracted from the parameters. So if the gradient is very low, that means the parameters will not be updated that much, especially if the learning rate is also low. So you now have a low gradient times a low learning rate. That would be a very low value. So typically that means you have gotten to a local minimum or a saddle point. So a saddle point is a point where there isn't much change either. But if you keep going for a long time, maybe it can flip over because there's still some points on the landscape that are lower than the saddle point. But it depends on the direction that your optimizer is moving. So those are things we will see more of. Okay. The other thing is, yeah, gradient-based stopping is also common in a lot of the scientific machine learning frameworks that we use. So those are stopping methods. Okay, now we will talk about model search and optimization. So remember, like I said earlier, you can measure a model's performance, but what do you do with it? The most important thing is that can I improve the model performance? After I've trained this model, I now measure it. Would I have done better with a different architecture or with a different approach? Okay. So if you look at this machine learning pipeline, you see that we start with data collection, data cleaning, feature engineering, model selection. Model selection actually matters. Sometimes you do model selection um, before you even begin training because the reason why it is valuable or important to do model selection before you begin training is because sometimes if you may have the need, the requirement is so much, the amount of computation is so much, right? Um, for you to train this model. So will it make sense for you to spend all that compute, and all that time to train a model on an architecture that is probably not the best for it? That is a question. So in that kind of situation, the question would be, maybe I should first of all try different model architectures to find the one that is best suited for this specific problem before I come and invest time, compute, and other resources in training this model. So this is very key and is the whole idea behind the model search. So the model search is the key element in this, right? And we're going to talk about the different approaches that we use for model search. So after model selection, right, which goes through model search, sometimes you can actually select models based on your own experience with models. You don't need to do search, right? I know this is going to be the best model for this problem. Okay, but there are other times when you cannot decide. So you now use a more formal approach for your model selection. And we're going to talk about the formal approaches. So after that, then we have hyperparameter optimization, and then we'll have the model evaluation, and then we'll deploy. So hyperparameter optimization is another part of it, right? You want to figure out the best hyperparameters for training the models. Sometimes this involves training the whole model, right? And then on a particular set of hyperparameters, and then we pick another set of models and we train. Or it might involve doing a pre-step. After you have selected model, you do another step to select the hyperparameters, the best hyperparameter for the best model that came out of this, right? Before you do the evaluation and deployment. Evaluation is actually part of the selection and hyperparameter optimization process. So one of the things that you observe is that you could have very good data, excellent data, but you choose a bad model or a wrong model or a wrong architecture or a wrong approach, right? You still end up with bad performance, even with good data, right? That's the first thing. Then the second thing is you could even have a good model and you have good data, but you pick the wrong hyperparameters or poor hyperparameters. You're going to end up with suboptimal results. Yes, because you picked a good model, it's going to be good. But you could have been much, much better if you had tuned the hyperparameters that you use for training the models. Okay. Then of course, in that case, you get much better results if you are able to optimize and tune the hyperparameters properly. So what is model search? Model search is the process of finding one, the best algorithm. Am I using logistic regression or random forest? Am I using XGBoost or support vector classifier, support vector machines, or any of a whole bunch? Because there's a whole lot of different approaches that you could use. So the question is, which of them am I using? And then after you have selected that, the next thing in model search is, what is the best hyperparameters that I can use to train this model to get the out outcome that I want, or to get the best outcome? So that also means you will do some work as well. And then you have identified the best hyperparameters. The other question will be, are these the best feature set, especially if you're using fast approach? Like I said before, with neural networks, you probably don't need to worry too much about that. Neural networks will essentially feature engineer the features they need. We talked about that when we talked about representation learning. So, but for simple problems where you're using classical algorithms, you typically want to also figure out what is the best feature set. So at the end of the day, the question is, which model should we deploy? And this which model covers all these three items. So there needs to be a systematic way of comparing it, right? And we're going to look into that. So that's really what model search and optimization is about. So first of all, we need to understand the difference between parameters and hyperparameters. So we have been using this terminology a lot, and I just want to be sure that everyone really understands what these things mean. So when we say parameters, we know parameters to be the coefficients of the linear equations, right? That are essentially represent all of these those coefficients, the M1, M2, or beta 1, beta 2, or whatever, we want. Those are the parameters. Those are the coefficients that combine with the actual inputs, the features, the X1, X2, and so on. Those form the features. So when the features X1, X2 combine in a sum product with the parameters, which are the M1, M2s, then it gives you a linear sum. And then you have a system of such linear equations that effectively make up that model. So, and then of course, system of linear equations can then be passed through anything. It could be a nonlinearity, it could be an optimization function, or it could be a sigmoid function, or whatever it is, right? But at the end of the day, that's what they all do. So those are the parameters, and those are the values that you adjust, right? Those are the values that you adjust when you're training the model. When you say model is learning, that is what is changing, because learning implies something is changing, something is improving and getting better. And the things that are getting better are those parameters. So in the linear regression problem, like I said, parameters refer to the coefficients of the linear equation, right? In neural networks, parameters refer to the weights and biases, which are still coefficients of linear equations that are, inside the internal neural network model, right? So that's the parameter. For decision trees, yeah, decision trees are not based on a system of linear equations. Rather, they are based on a simple comparison of, is it above the threshold or below the threshold? If it's above, it goes to the right side. If it's below, it goes to the left side. So what forms the parameter then is the threshold. And at every node, at every point in the tree where you're making a decision, you are learning a separate threshold for each node, um, going through the decision tree algorithm. So that means the threshold I use to split, essentially, that is the parameter. Okay. So the parameter is what changes while you are training. But for hyperparameters don't change while you are training. Hyperparameters are those values that you use to even determine the model's architecture or the, the way the model is getting trained. Okay? The way the model is getting trained. So you have to know the hyperparameter before you start training. Unlike parameters that you start with any random values or any values of choice, sometimes zeros, sometimes any value of choice, sometimes random values. Okay. And eventually the parameters will converge. When we say converge, the parameters will end up assuming values that will work with the that work towards the prediction that we want. Okay. But hyperparameters, you have to choose the right value at the beginning. If you choose the wrong value of hyperparameters, you never get it. So for example, if you choose a very high learning rate is one of the hyperparameters, you end up with you know, um, gradients that blow up and your model never learns. Okay. So other hyperparameters, what most people don't even know is that a parameter or a value like the number of epochs you use can also be considered a hyperparameter, right? Because it also influences what your model is learning. Parameters like there are parameters that directly affect the learning of the model. For example, the learning rate. For example, the number of estimators in a random forest or any other um, ensemble approach. The max depth, right? And others for support vector machines, the C, which is the penalty, right? For um or the distance from the it's the penalty, right? Which is basically how much impurity that you allow, how much of items from the opposite or from the other class that you allow across the decision boundary, right? Even the kernel that you choose is also a hyperparameter, right? The number of epochs is a hyperparameter in a way, even though you could say infinite epochs. So in that case, it learns. So the epochs no more becomes a hyperparameter because it doesn't affect the learning anymore. Well, in that case, the other parameters that you use to stop training become hyperparameters. For example, the early stopping threshold, right? Or the early stopping patience, for example, right? Or even if you're doing a plateau-based stopping like we just saw, the uh, the you know the band, right? The error band for stopping if the model doesn't learn anymore. In other words, if the loss doesn't increase anymore, right? Or if the increase in the loss is lower than a minimum value. So those are all the examples of hyperparameters. So the hyperparameters still affect how well your model learns. Okay. And that is why it is very important to be able to figure out the right hyperparameters. But unlike parameters, which are part of what your model is learning, it's not that easy for you to pick hyperparameters, right? Picking the right hyperparameter will affect how well your model does. So I'm going to use this simple example to show you the impact of hyperparameters. We'll use a random forest classifier and we'll try to solve a problem that is somewhat complex. Okay. So the random forest classifier, we are going to try two examples. The first one is going to have only 10 estimators and a max depth of 3. 10 estimators means only 10 trees, 10 decision trees. So it doesn't have a lot of capacity, right? It's the same algorithm, different settings, right? But the performance will be very different. But the first one doesn't have enough capacity, but it didn't give it enough estimators. And the max depth is also not enough for it to be able to separate properly the different features, right, in the data. But we'll compare that with a random forest classifier where the number of estimators is 500, which is basically 50 times more. 50 times more trees. Max depth is 20, right? This one, by the way, will take longer to train because it has a lot more um, you know, trees and the depth is much more. But you find that this will do better. Okay. That is what you find. So sometimes the idea is this one might be too much It might be too complex. It might even be overfitting on the data, which is typically what happens with random forests, right? But this one might be too small. So the question is, how do I find the right points, the right um, set of values to choose? And you can see here there are two sets of values to choose from. In some models, you even have more than two sets of values. Okay, so should I be manually trying them one by one? Which value should I even try? Should I try 10, 11, 12, 13? How can I be able to try all of the numbers or possible number of estimators between 10 and 500? How about max depth? So these are the questions that you find, okay, that you have to figure out. So underfitting means your model is too simple. Typically, if you're underfitting, that means the model is too simple, it's too small. The capacity of the model is too small for the data, right? Or for the relationships in the data. So you typically end up with very high training error and very high testing error. This is something to take note of, right? As a matter of fact, if you are to plot a loss curve of training for a model that is underfitting, and that's why I always ask for us to plot loss curves. If you were to plot a loss curve for a model that's underfitting, it will look something like this. You have you basically have it you know teeing up at this point. This will be the training the validation loss. Validation loss typically is might even begin going up if it's overfitting, but in this case, it's not overfitting, it's underfitting. So you could have something like this. This is a training loss. Training loss would be would not go as low as it should, probably, you know, somewhere here. And if you were to do the validation loss as well, you may find that the validation loss also kind of tracks the training loss somehow. And, you know, so it doesn't come all the way down. That's the main thing you see when you have underfitting. But when you have overfitting, you have a different scenario. In this case, your model has a large capacity. In fact, it has more capacity than the data, right? Because it has more capacity than the data, then there's going to be a tendency for it to overfit the data. And what I mean by overfit is it's going to learn specifics of the data instead of learning the general trend. And when it starts learning specifics in the training data, things that are not in the nature of the data itself, maybe it starts learning noise and so on. Then if you give it data that is not in its training set, okay, it begins to fail. It doesn't do as well. So when you have a model that is overfitting, you tend to have something like this, where the loss actually drops really close, to a low minimum. But that's for training loss. But for validation loss, you will now see that validation loss would tend to um, go, but at some point, it may even begin to go back upwards, right? And the reason why it's going back upwards is that the overfitting is making your model get better and better at this specific data, but it's also adjusting away from the generic knowledge it should have. So you're getting worse on the generic knowledge because, the thing is that there's what we call capacity, right, which I just mentioned in models. And when you talk about capacity, the capacity is fixed. Once you have picked your model architecture and the number of parameters in it, that's the capacity, right? So it can use that capacity in one way or the other. If it uses that capacity in learning things that are specific to the training data, then it will lose the knowledge that it may have learned on things that are generic or general and uh, it would have helped it to do a good prediction on data that is not in the training set. So it will get worse in that regard. So the goal with hyperparameter tuning is that you want to find a point where the training error is low and the testing error is also low. So effectively, you don't want overfitting, you don't want underfitting. You just want a model that gets it right all the time. So even if you are training, ideally, when you pick the right hyperparameters, no matter how long you train, right, you will always have a situation where the model is effectively it doesn't overfit, right? No matter how long you train. In fact, a lot of people have asked me before, um, should you always allow a model to train, infinitely for a long time? Ideally, if your model was good, it be um really shouldn't be overfitting or underfitting for that matter. If your model is well designed, you choose the right architecture and you choose the right number of parameters for the data sets for the problem that you are working on, then your model should be quite okay, no matter how long you train it. The worst that will happen is that it will stop improving, right? It will just flatten out as a plateau, but it will not get worse. It's not supposed to get worse on the validation data. But if that happens where your model gets worse on validation data, then what that means basically is that you choose a model that was too big. Well, sometimes you don't have a choice, right? The data might have been inadequate, or we need to get more data. So that's the other thing. So that is that is um that is hyperparameter tuning. Um, I think I'll just do all the hands-on all at once. So let's just go through all the theory and then I'll do the hands-on after. Now, um, the other thing that we talk about is cross-validation. When you're comparing different models, there's what we call cross-validation. It's a technique that you use for evaluating model performance by splitting data into multiple train test partitions. Cross-validation is a way for you to eliminate skews, biases, right? Unevenness in the training data or in the data that, yeah, well, not the training set specifically, but the entire data set. Okay. Some unevenness in the data set that you are using to train your model. And the reason for this is sometimes if you do a single train test split, it might be unreliable. You might have a situation where you have a lot of particular data of particular type is bunched somewhere. And this is sometimes an issue when you cannot shuffle the data. Typically, you could solve or overcome this problem by shuffling the data, right? And if you have a good shuffling algorithm, then you have a good mix of all the data. But there is also the challenge that sometimes it that shuffling may not even work because if you have an unevenly distributed data where you have like what we talked about last time, you have one class that is far more in number than the other class. For example, think of a data set where the yes is 90% of the data and the no is 10%, right? In a label data set, or the ones are 90% and the zeros are 10%. No matter how you shuffle that, right, there will always be a tendency for, for you to have a lot of those numbers, the zeros that are very few in number. You may have a bunch of them in one split. So if you do train test split, you may actually have a lot of zeros on the train side and the test you don't have any. Okay. Or you may, well, that's not even bad, right? What would be worse is if you have most of the zeros on the test side, I don't have enough on the train side of the split. And when you train, your model never has enough data to actually learn the negative side of the prediction. Okay. So that will always lead to some kind of unreliability. So how do you solve that? Okay, the other thing would be if you have a very large data set that is impractical for you to shuffle. It's impractical to shuffle. So you are just loading data set as it comes and you are doing your test train split. Yeah, you can shuffle within the small batch that you loaded and do your test train split. Okay. So that there can be situations where that is unreliable for you to do just a single test train split. For example, you do a test train split of 80-20, like what you're seeing here, right? And then a lot of the items go into the 20 side, which is the test. So what cross-validation does is that um well, you are doing it because you want to it effectively does multiple test train split. We'll look at that methodology later. But the reason why cross-validation came up as a method and why we want to do cross-validation is that unreliability I just talked about. The fact that with cross-validation, you can also reduce the variance when you are doing your performance estimate. Because remember, you are doing your performance estimate, you are doing it with the test data or the validation data, right? So when you use cross-validation, you kind of even that out a bit. Then it also helps to detect overfitting, right? It helps to detect overfitting. It works well for small and medium data sets. It improves robustness of your model selection because you are evaluating your model on, you are eliminating basically noise, right, in the data set or noise that comes from the way you split your test train, um, you know, sections. You have more reliable estimates, right? And if you have limited data, it allows you to use your limited data much better. So what you do with cross-validation, the most common version of cross-validation is what we call the K-fold cross-validation. So why it's K-fold is that you take the data. So typically, if you are doing test train splitting, you would normally take the data and you would split it into the percentage that we just mentioned. Maybe you would split out 20% of it, for example. So 20% is 1/5. So 20% is 1/5. So if I take out 1/5, maybe somewhere here, this is a line. And if I do that, then this part of it becomes the test data. So the 20% becomes the test data. Okay. And like I say, you could have a situation where you have kind of skew on this side. So with K-fold, instead of just doing a simple 80-20 split, with K-fold, you divide this into 5. So you divide into 5 equal sections or batches, right? And then when you divide that 5, you then use each of the 5 that you have divided as a test, um, you know, as the test part, use it for testing. And then you use the remaining 4 for training. So what will happen is that the first time that you are training the model, you use the first one for your tests and then use the rest for training. The first of the 5 equal. By the way, it's 5 equal. I didn't really draw it very well here to indicate that equality, but it is. So the first time you train, you take this and you use it as your um, test set, while the remaining 4 will be used for training. And then you complete training. You pick whatever epochs, you train, you finish, and you test. So you test on this one, you train on the remaining 4. Or you start from the end, whichever one, right, as you choose. Then when you finish that, you do another round of training. So in this other round of training, you choose this second set. By the way, you don't change the sets. You choose the second set, and that's what you will use for training. While the remaining ones use this small piece for testing, while the remaining 4/5 will be used for training. So you're still having an 80%, 20% split, right? But what is now changing is which of these sections are we using as the 20% for the testing data. So you do a third one, and you use this other one now for testing, while the remaining four will be used for training. Okay. And then you do another round again, the fourth iteration. This time I use this one for testing and then use the other remaining ones for training. And then after that, you do a fifth one. So that means you're going to run this training 5 different times. And each time you train, you are going to use the same 80-20 split. The only difference is that the 20% keeps changing, which one you use for the 20%. And then, of course, the balance is what you use for the 80%. You could also look at it the other way, which one you use for the training. And then, of course, the balance is what you use for testing. So what this does is that it really improves the distribution, because it means that each of the tests and training get to see um, um, the other as well. Even though in a way you could also say, am I not training models? Am I not training the model on test data? Now that's not really correct, because each time for each round that you are doing, you're training a new model. You're not training the same model. Right? You are training a new model. If you were to take the same model and do this cross-validation, then it is invalid, because effectively you are now training the models on the test data. But the idea is that you are going to do validation with the test data. When I go for the first time I do it, it's a new model. The second time I go for it, I start with a new model from scratch with random weights and retrain, not the model that's already been trained. And you do that. So you're going to end up with 5 different models. And then those 5 different models will now calculate validation errors on them, and then compare the validation errors on them, and perhaps take the average value of the validation errors from those 5 different folds. Okay. And that is what we will now use as our overall validation error. So that is what k-fold cross-validation means. And the question you might be asking, why would I go through all of this? Just to eliminate biases and distribution error. This is when it comes to machine learning, we always try to be very careful, because a lot of biases that come into your training can actually result in in errors or in wrong selection, especially when you consider the difference between one model and the next might just be 1% accuracy or 2%. One might be 92%, the other one is 94 or 93. And we are saying, okay, which of these models should we choose? Now, what if there was some kind of skew, especially, yes, which model are we choosing? If you do not do cross-validation, you might end up with a model that's unlucky in the distribution of test train splits that was used to train it. And it looks like that model was, it's a bad model, when actually it was just unlucky. So that's what it is. And the common values we can use for K, you can see if you use K of 5, then you're going to have an 80-20 split. If you have a K of 10, then that means you are dividing the data into 10 sets, right? And each set is going to be 10%. So that means you're having a train test split of 90-10 if you are using K of 10. So those are the 2 common values I used. Then we have other variants of K-fold cross-validation. You have the stratified K-fold cross-validation, where you try to preserve the balance of the classes in the different groups when you are splitting them, right? You try to maintain the balance. Like I said, if you had a categorization, a category that you have one class that was far more than the other, then Stratify will try to ensure that you have equal proportion. Let's say if we use the breast cancer example, um, you have malignant and benign, right? Malignant and benign. And you have 10% malignant and 90% benign. Then when you are dividing your test train data, you always try to ensure that that proportion of 10, 9 is to 1 is maintained even in the subdivisions that you have created. That's stratified k-fold. Then repeated k-fold is you are just repeating process multiple times. Then you have a time series split. This is really useful for time series data. So you have to order it past to future when you are splitting. So you have to order it past to future. And also when you are it now matters, right? The chronology matters as well. Okay, so that is cross-validation. We're also going to touch a little bit on it. So cross-validation helps you to, when you're doing validation, to be more thorough when you are comparing different methods. Okay, so now we want to talk about exhaustive search or grid search. Grid search is a technique that you use to find the optimal settings for a model, right? So grid search is where you can you systematically build a grid of all possible combinations of parameter values, right? Or hyperparameter values rather, not parameter values, because you cannot really do anything with parameter values. So it's all possible combinations of hyperparameter values, right? And then you now evaluate the model on each combination to find which one yields the highest accuracy, right? Okay, let me step back. Actually, it is correct. It is all possible combination of parameter values, right? So grid search, well, you can it's hyperparameters effectively. It's hyperparameters, but it's parameters that are sent to sklearn. So you are looking at hyperparameters, and typically grid search is used for finding hyperparameters. But you can also use grid search, right, to find um the best model. Even though if you want to find the best model, you typically do a model search, right? But then model search basically means you take all the models you want to try out and you essentially run the same data set on them and then you measure their performance. And typically you may want to say, okay, let's run them with the default hyperparameters for each model. Even though you could also tune each model to get the best hyperparameter. So that's an interesting thing. The question would be, if I'm doing a model search, should I go with default hyperparameters and then get the best model from there and then tune that best model to get the best hyperparameters that for that model? Or should I tune hyperparameters for each model to get the best combination of hyperparameters? And then after that, I do a model comparison. But then again, by the time you do hyperparameter tuning for all of the models, you already have your answer anyway. But the problem with trying to do grid search on every single model that you are trying to choose from is that's a lot of work. That's a lot of work. Just doing grid search on one model architecture alone. For example, we do grid search on random forest alone, might be up to, thousands of different combinations or permutations of the hyperparameters. So imagine having to do that for another 10 different model architectures. But then that could be the thing you want to do because I want to get the best, right? So um, that can be the case as well. Okay, so grid search is called exhaustive search, right? The reason why it's called exhaustive search is that you are trying every possible combination of the hyperparameters. You're trying every possible combination of hyperparameters. And um, it takes a long time because the combination of hyperparameters can be a lot. depending on the granularity that you decide to go with, right? Um, you may decide to go with very low, very high granularity. Very high granularity would effectively mean that maybe you are every 10 steps or every 5 steps or every one step, right? But lower granularity would be maybe every 100 steps or 1,000 steps. Okay. But there's a tendency that you could miss the best value if your granularity is not high enough. Okay. So um yeah, so grid search will take every single combination and permutation of every hyperparameter, right? And will now run training and evaluation, right? So grid search is effectively a brute force approach, a brute force approach. And I hope you know what brute force means. In computer science, brute force means you're not even trying to fine-tune the algorithm. You're just basically searching every possibility. That's what brute force means. And the reason why it's called brute force is there's no thinking around it. If I want to check, for example, which is the best of a million options, I try every single one of the million options until I find the best. Of course, I will not find the best until I've tried all the 1 million, and then I'll select the best from there. So the reason why it's brute force is there is no attempts to, improve or do anything fancy with the algorithm. You just search everything. So typically that's what it's called brute force search. So well, grid search is not really brute force per se, because even in the fact that you are trying all combinations and permutations, but it's not all possible combinations and permutations. You still limit it. You still choose which ones you combine, but it's still kind of brute force. Um, and it's quite effective. So the advantage is it is exhaustive. It will search every single combination, based on what you provide. So it guarantees that you'll find the absolute best combination within the specific values you provided. That is very important, right? I needed to point that out. And that's why I said it is not entirely brute force. Because if you do not specify all possible values, then it may not really come up with. So there's a bit of domain experience that you need to have to know which one to pick, right? So that's one. The second thing is that, yes, it is automated. So you don't need to guess, right? There is no guesswork. It just runs the calculation and gives you the best set of hyperparameters. Also, because sklearn provides an algorithm for it, provides a class for it, you don't need to do all of this yourself. You could have done it yourself, by the way, by just writing nested for loops, okay, to test those parameters. But you just give the parameters and the hyperparameters, and it does that. However, the disadvantage of this approach is that it is computationally expensive because you are trying out every single combination and for that same reason and permutation of the hyperparameters. So for each combination of the hyperparameters, it must create a model, it must train the model, then it must evaluate the model. So that can take a massive amount of time and processing power, especially if the model is large, very large, or the data set is very large. So it's typically not a very good idea for such kind of things, right? Then the second problem or disadvantage of this approach is the cost of dimensionality, which basically what it means is that the more dimensions you add to the problem space, it blows up, it's exponential, right? So if you add more parameters or hyperparameters, okay, or you add more values to the existing hyperparameters that you have specified, the amount explodes. So for example, well, we'll see it in the next slide. So those are the two main disadvantages. So here's an example of grid search. So let's assume you have a random forest and you want to basically figure out what max depth to use and number of estimators. Remember, we just talked about here where you would tune. I have two of them here. I would tune. Well, or I'll compare their performance. But I now want to find the best of these parameters to use, the number of estimators and the max depth. So with grid search, I could then go through the approach of specifying all of the possible max depth I want to try out. In this case, just three is specified. And then I'll specify all of the possible number of estimators I want to try out. So with this, because I have three max depth and three estimator counts that I want to try, the total number of combination of parameters here is 3 times 3, which is 9. So there will be 9 experiments that the grid search will have to run, right? So it's going to essentially create um, it's going to essentially create 9 different random forest classifiers and train them with each of the 9 combinations. And then it will now do an evaluation to measure which one performs best on the test data. Or if you give it the whole data, right, it will do that. And then um, after that, it will now come up with the one that performs the most. Okay. So now think about if I decided I wanted to, instead of using 100, 200, 500, I used 100, 200, 300, 400, 500, or I started from 10, 10, 20, 30, 40. So you see the number of experiments will begin to explode. If I had 100 different values for n estimators I want to try, and I had, 10 different values of max depth I want to try, that's 10,000, that's 1,000 experiments. If there's another hyperparameter, then I'll still multiply by that third hyperparameter, a number of different values I want to try. So you can see how this can blow up and become very large. So when you are doing grid search, one of the important things to note is you have to be very, you know, wise in how you select which values you want to test. There has to be a little bit of sense around it, so it cannot be unbounded. Okay. So the method is generally defining which parameters that you want to tune, which hyperparameters. So for example, the learning rate, the tree depth, regularization strength. And sometimes you do not tune all of them at once because there are so many hyperparameters. Let's assume you had 5 hyperparameters, and then each of them had 10 different values that you wanted to try out. That's 10 times 10 times 10 times 10. That's 10 raised to the power 5, right? 10 raised to the power 5, that's 100, that's 1 million, or 100,000, that's 100,000. So you're talking about 100,000 experiments just for 10 each. So typically that would take a lot of compute, a lot of time. So typically what you may want to do is, okay, let me keep a few of them constant and vary a few of them, right? That way you can control things. And then when you have gotten the best value for the ones that you were varying, you can then keep it constant at that base value and vary the other ones. Even though it's possible that that's not really exhaustive because that may miss some combinations that would be better. Okay. But again, it all comes down to experience and a bit of domain knowledge. So when you pick those ones, right, you pick which ones you want to test, you pick the specific values, then you build a grid. So the grid is basically a dictionary like this that contains the name of the parameter and a list of the different values for that particular parameter you want to try. So that's what makes it a grid. Okay. So when you do that and you pass it, you use this grid search CV, which is the grid search algorithm that sklearn provides for us under the model selection sub package. Okay. So you specify what type of you know, algorithm that you want to optimize for. And you actually have to create an instance of it, in this case, random forest classifier. Then you specify the parameter grid, which is basically that list of parameters and the values. And then you can add other things. So in this case, you have a scoring here, which you specify how you want to score. You could use F1, which is the F1 score, or recall, or any of them. You choose what you want to use. And CV is cross-validation. So cross-validation, like we talked about, when it is even doing the scoring, it's going to use cross-validation. So it's not going to just train a single instance for each parameter that you're tuning. It's going to use a cross-validation k-fold. Basically, CV is saying five-fold cross-validation. So you can see how it can become very computationally expensive, but that really helps, right? It really helps. So the second step is build the grid based on these parameters that you provide. Then the third step is it now does evaluation. So it trains a new model for every combination on the grid and then calculates its performance using a validation set. If you give a validation set, or it uses cross-validation. In this case, we did not provide a validation set, right? When you run fit, we just provided the training and white train, X train and white train. So it's going to take this X train and white train and use cross-validation on it. So it's going to take it, split it into five subsets, and then train on four of those and test with one. Then the next one again, train on another four of those and test with another one that is different from the first one and so on, like I explained during cross-validation. And when it has done all of that, right, cross-validation and then every parameter, it now comes out with the best. So it tells you which is the best combination of hyperparameters that provided the best score that you had given here. And that's how you do grid search. You can see it's if you look at under the hood, this is really complex. There's a lot going on, like I've tried to explain. But sklearn takes all of that away from you. So you just call the functions and you run grid.fit. Same signature, just fit. And then when you do fit, you can then calculate the best params, which will give you the best parameters from what you have in this list or in this dictionary, and then the best score. So this tells you kind of how it is doing that. When it's doing that, it trains a model with 5 max depth and 100. Then, so it trains 3 models with 5 max depth and 100, 200, 500. Then when it's done with that, it starts to train another model, but this time around max depth of 10. And then starts again with 100 number of estimators. So that's the different permutation. It keeps going that way until it exhausts all the combinations. So that's grid search. Then we also have random search, which is another search model search approach. Random search is a bit different from grid search. Unlike grid search that will search every possible combination, random search would take only a few and randomly select. So you give it those same that same grid, right? But it's not going to select all of them. It is rather going to just randomly pick. So from this 1,000 possible combinations, going to pick maybe only 50 and use that. So it's random. The advantage is that it's faster, right? Often it finds near optimal solutions. It comes close, right? Because it's random, right? Um, but yeah, it works well when you have high dimensions. Yes, if you have a lot of dimensions, like I just talked about 100,000 different permutations and combinations, it is not practical for you to talk about grid search. So in that situation, it's probably better for you to just go with random search, where you go for a smaller percentage of the space, or you specify the number that you want to search, and you're going to randomly pick that number and do that training. So this is also very good for use when your parameter space or hyperparameter space is large. But one of the things you find out is that a lot of hyperparameters don't have a lot of impact. So um, random search will spend more time exploring important regions or important parts of the hyperparameter space. Okay. Then there is also Bayesian optimization. This is another method, right? Um, so with Bayesian optimization, what you do is you train a model and you evaluate it. Then based on the results, okay, you kind of try to make an educated guess, or the algorithm tries to make an educated guess of what's the next set of hyperparameters I should use. Okay. So instead of an exhaustive search, which is what the grid search does, or just random search, which sometimes can miss very key combinations of hyperparameters, what the Bayesian optimization does is that it's going to build a model that it will use to predict what would likely be the next best set of hyperparameters to pick from. And that's very interesting because you now have a model that you are not training, the model is learning not to predict something else, it's learning to predict what is the next best hyperparameter combination that it should use. That's how, that's like a second level of inception, second level of modeling. So the Bayesian optimization is a model. It will try a few different hyperparameters, maybe initially, and then from there it gets an idea and begins to form um it's a probabilistic model. So it begins to form an idea of, okay, this is likely going to be the next best one to try, and it tries it. And based on the outcome from that one, it improves the model so the model gets more accurate, and it tries the next set of hyperparameters. Again, still from that original set that you create from that in the original space. Yeah, so it balances exploration and exploitation. I'm not going to go too much into this, but this is basically saying exploration is when it's trying to look for what is going to be like the best set of hyperparameters, while exploitation is using those particular hyperparameters to train a model. So it kind of balances that because if it uses every single one to train a model, it's going to be slow. It's going to end up being almost like exhaustive search. So it won't do that. Rather, it will sometimes um, try to find other combinations of hyperparameters in that entire hyperparameter space. So Bayesian optimization is very useful for neural networks for XGBoost tuning, if you are tuning hyperparameters with XGBoost, and for expensive experiments. These are experiments, when we say expensive, they take a lot of computational power. So for you to train one model, to finish training one model, it's going to take a lot. So you don't want to just train models anyhow and evaluate only to throw it away and say, oh, this one did not perform well, right? And these are libraries that allow you to do that. So these don't come with the sklearn. You use Optuna, HyperOpt, and Bayesian optimization. So when you compare all of these, the three methods for model search that we have talked about, you find that the first one, grid search, is speed is slow because it's basically testing every single thing. But search quality is excellent. It must find it. The complexity is low. It's just that's why it's a grid search. It searches every single possibility. Random search is faster, right? Search quality is very good because even though it's random, but it's highly probable that it will get an optimal outcome. But complexity again is low. It just takes a random subset of the original grid space. Okay. Bayesian optimization is fast again, and the search quality is excellent because it is using a predictive model, a probabilistic predictive model to choose which hyperparameter combinations to test. It's not just random. So it's definitely going to be better than random, right? And it could be as good as grid search. After a few attempts, it kind of already forms a model that it can use to predict, right? And the complexity is kind of medium in the sense that, yeah, it's kind of using another machine learning model. So think about that. You're using a machine learning model to figure out the hyperparameters for other machine learning models. Then we have evolutionary algorithms. I've not talked about these ones, but evolutionary algorithms, I think one of the ones that I used to a lot in those days, I don't know if I still use now, is what we call genetic algorithms, right? So with genetic algorithms, what you would do is you would basically train models and see how well they perform against each other, right, in an environment. It's kind of a complex system, but again, it always results. There are other kinds of evolution algorithms as well. So the recommendation here is this. If you have a small search space, right? That is maybe less than 1,000, I don't know, 100 to 1,000, you can use a grid search. You get it's slower, but you still get your result. If you have a large search space, then use random search, right? Random search you can still limit the number and still get almost as good an outcome. If you have expensive models, then use Bayesian optimization. And why this is so is expensive. Bayesian optimization does not always try to evaluate the models all the time, right? Or train the models and then evaluate them all the time. Sometimes it just uses its internal model that it has learned of being able to predict which hyperparameters will be best. And it uses that. Sometimes it does more of searching for which hyperparameters will be best than evaluating it. Okay, so when we are doing grid search, one last thing is um, what are the things that you look at when you are doing model search? How do you measure? So I think we've talked about that, so I'm not going to dwell on this. But for classification problems, you use accuracy, precision, recall, F1 score, and the ROC-AUC. So ROC-AUC is the receiver operating characteristic area under the curve. Basically, it's a standard performance metrics that you use for evaluating binary classification models, right? It measures how well the model can distinguish between two classes. So it's kind of similar to, it measures how well it does with the decision boundary. That's it. So it's a very long name. And we also have this available in SQL. If you are doing regression, they use MAE, absolute error, MSE, max square error, RMSE, mean, minimum absolute error, minimum square error, mean, not minimum, mean absolute error. That's the average absolute error. Then minimum mean square error, and then the root mean square error. So we've already talked about all of this. I wonder why I'm mixing up the names. Then we have the R squared, which is the coefficient of fit, basically. So the important thing is that the metrics that you choose should be the ones that will align with business goals. And we talked about this when we were talking about evaluation. Okay. If you are doing malware detection, for example, um, where false negatives are costly. False negative is where it wrongly detected it as not malware. It is malware, but it wrongly detected it as not malware. So that's costly because effectively it's going to cause problems in your system. Effectively, it's a loophole in your cybersecurity system. So for those ones, you use recall because recall gives you a better measure of how many you failed to classify correctly, right? How many you failed to classify correctly is measured by recall. How many you classified wrongly is measured by precision. Okay. So in a case where how many you failed to classify correctly is the key thing, you use recall because recall is a measure of how many you correctly classified as true divided by how many you wrongly classified as true plus how many you wrongly classified as false. Okay. Sorry, how many you correctly classified as true and how many you wrongly classified as false. In other words, how many are true, but you wrongly classified it. So that gives you an idea of performance across false negatives. But false positives are the ones that you wrongly classify as true. And you use precision because precision is a measure of how many you correctly classify as true, or how many your model correctly classify as true, divided by how many your model classified as true plus how many it wrongly classified as true. So that is precision and recall. So the metric that you choose depends on what you are training that model to do. So It is very, very key. In fact, I'm going to ask us to do a few exercises on that so that we can think about it. In modern times, we also use AutoML as a way for model selection. It's automated. It can automate the model selection. It can automate the hyperparameter tuning. It can automate feature engineering. It can automate the ensemble construction. So there are many of them. For example, AutoScaling can do AutoML. So it's something to look at. Teapot, Optina, and Raytune. And the applications where we use this: healthcare, finance, cybersecurity, and scientific research. And typically, the auto ML is at the point of model selection. You now have another process going on, cycling until the correct model is identified, and then before you now evaluate the model. Of course, in the process of identify the model, there's some training. Sometimes you don't train the model to the full, right? You train it to a certain point because there might not be enough resources or compute to train the model to the full. So you train it to a certain point. Okay, so that's all about model selection and optimization. Now let's talk a little bit about bias and variance trade-off. So what is bias? When you're training a model, bias is a measure of the error that your model is making from incorrect assumptions. And typically happens because the model did not train enough, right? Or the model does not have enough capacity to learn the complexities and the complex relationships in the data. So if you have a model that's too simple, it underfits. So a very good example of bias would be if you have a linear model and you're trying to fit the linear model on an exclusive OR problem, for example, right? Or you're trying to fit the model on a problem that has a circular decision boundary, then you have a problem. So let me show you how that looks like. Let's assume you do a simple linear regression model and you want your model to fit, on what we call the exclusive OR problem, which we'll also talk about when we talk about neural networks and perceptrons. So the exclusive OR problem is a case where you typically will have four values with the exclusive OR problem, and it is not linearly separable. What linearly separable means is that you cannot draw a single straight line and create an adequate decision boundary that correctly separates those models. So let's look at this as an example. You have red and you have blues, okay? The exclusive OR problem can easily be represented this way. What we say is a truth table, if you remember that kind of a thing. Where we say true and true equals what? True. True and true equals false. That's exclusive OR. False and true is true. Sorry, and not an or. False XOR. So this is the XOR problem. Let's see if I can explain it. So this is the XOR problem. XOR. That's why it's called exclusive OR. If you look at a truth table, for those who have done a little bit of computer science, all right, you have four states, right? We normally call it A, B, and then A exclusive or B. Unfortunately, I don't have, I might bring this up. We'll bring this up when we're dealing with neural networks. So A exclusive or B. This is typically a symbol of exclusive or. It's just a circle with a plus in. So if A is true, is zero, rather, A is false and B is false, then A exclusive or B is false. Then if A is false and B is true, that is one, then A exclusive or B is one, right? If A is one, that is true, and B is zero, that is false, then the exclusive OR is also one. And then when both of them are true, A is one and B is one, right? Then exclusive OR is zero. So in other words, this is kind of the implicit logic. We used to call it implicit logic that says, um, A or B, either A or B, exclusive or. So if you plot that on a graph, right? And let's assume that this is on this graph, this is A, this line is A, and this other line is B. So that's how you're plotting this on a two-dimensional space so that we can have a decision boundary. And then we say there are just two values. So this is where A is 0, right? And this is where A is 1, okay? And then this is where B is 0, and this is where B is 1. So we now plot it. So we're essentially plotting that, what I just said now on a graph. So we plot it on a graph, and what you now see is, of course, when A is 0 and B is 0, that is this point here. I want to use a different color. So when A is 0 and B is 0, that is this point. Uh, use pink. So when A is 0 and B is 0, right? Blue means 0, okay? So the XOR of the two is 0. When A is 0 and B is 1, then it is red. So red means 1, okay? Then when A is 1 and B is 0, right? It is also 1. So that's why it's also red. Remember, blue is 0, or blue is false and red is true. Then when both of them are 1, then it is false as well. So that's kind of thinking about it that way. So that's how you can see this chart. Now the question is this. This is somewhere we have to draw a decision boundary. And the question is, can I draw a single line to separate, to act as a decision boundary around these? Can I draw a straight line? It's impossible. You cannot separate this with a decision boundary. You cannot. You cannot. It's impossible because it's not this. You can't draw a straight line to separate the red from the blues. You can draw two straight lines, right? You can draw a circle. You can draw, well, maybe not a circle, maybe more like an oval. So you can draw any number of shapes. You can draw two straight lines like this, right? In which case, everything in between the straight line is red. So that solves it. But this is two straight lines, not a single straight line. You could draw a curve, right? And you could say, okay, that's a decision boundary. So you draw a curve like this, and you say that anything inside this curve is red, okay? And anything outside is blue, right? But you can't do this with a straight line. So you cannot, if you were to take a linear model and train it on this exclusive OR problem, it will never solve it. It will always underfit. If you calculate the loss after you have trained it, you always have a high value, relatively high value, right? That is what we mean by underfitting. So, underfitting in the situation, in this case of underfitting is caused by inadequacy of the model. In most cases, underfitting is actually caused by inadequacy of the model. This is the truth. In most cases, your underfitting is caused by a model that is not complex enough to represent the relationship between the data. So these are examples. So I just talked about that exclusive OR, and that's just exactly an example of a linear model, trying to use a linear model to model nonlinear data. But if we use a nonlinear model like a SVM support vector machine or something else, you will find that you can actually easily do that exclusive OR problem. Another example is if you have a shallow decision tree, the depth is not enough. So it cannot do a nonlinear thing. Okay. So typically symptoms of bias is a high training error and a high validation error. Both training error and validation error be high. because you cannot even train, even with the data training on it, it will not be able to get it. Okay. Now, on the other hand, variance is a case where the model learns very well the data that it is given, but it performs very well on the data that it was trained on. But if you bring test data that you separated and kept aside and you did not train on that data, it performs poorly, very badly on it, right? And the reason for that is because the model has learned too much of noise that is in the training data instead of learning the actual patterns. It's learning too much of noise. So a good example of that is if you had, um, let me see, I'll show you an example of that. If you had a model that maybe had a lot of data that where there's a bit of outliers and a bit of noise, and then your model is learning a decision boundary to follow. Let me show you an example. Let me show you an example of um, overfitting. I think I have it on this slide somewhere. So if you look at this, right, um, let me zoom in here so you can see this very well. I have this, and if you look at this specific drawing, you see that you have data. This is just a training data where you have reds meaning one class and blues meaning another class, right? Now, this is underfitting, okay? Because this is not a linear decision boundary. We're using a linear model here in this case, and the linear model is not able to properly separate. So you see these one, two, three that have been highlighted are misclassified. Now, you have a model that basically does this, right? This model is actually performing well on the training data because it is now fitting. Let's assume this one was an outlier or just some noisy sample. But your model has tried to adjust itself so much outside of what it should do in order to fit this data, right? So it will perform better on the training set, but on the test set, you find that it is not performing well on the test set because it was basically overfitting on the training set. So this is how you can think of a model that is having a high variance. The variance in this case means it is overfitting. It is learning too much of the knowledge in the data set, including the knowledge that is not generic across the entire data set, but the knowledge that is specific to a particular subset, right? So when you have variance, that typically means that the model is too complex and the data is too little. The data is not enough. So the model overfits. And if this happens because the model is too complex, what you normally would do is reduce the complexity of the model, right? Make it a smaller model. Um, so for example, if you're using a random forest, right, or a deep decision tree, and is overfitting, reduce the number of estimators in the random forest, reduce the number of trees, or reduce the depth of the decision tree, right? Reduce the complexity, reduce the capacity or the capability. If it's a neural network, reduce the number of parameters in that neural network. So those are examples. A decision tree is actually uh, always very likely to overfit. So that's one thing. Um, if you're having a polynomial regression and you have a high order, maybe fifth or sixth or tenth order, it might overfit. So you want to reduce it. So how do you know variance? Variance is as you're training the model, it is having low training error. The training error is actually getting better and better, lower and lower. But the validation error starts rising. So that is variance. So this chart tells you that there is a sweet spot. The best point when you stop training a model is that point where the total error is at the minimum. Because the total error is the error, the bias, right, plus the variance. This line here shows model complexity. So the more complex a model is, the higher it's likely to have a high variance, the higher likelihood, or the more likely it is to have high variance. It will have low bias, right, but high variance. Okay. While on the other hand, a model that is um, too simple, too small, insufficient will have a low variance but a high bias. Okay. So there's between these two extremes of a very complex model, or sorry, a very simple model and a very complex model, you will find a model that has the right level of parameters, the right level of complexity that will give you the best performance. So when you are selecting models, this is still part of model selection, you also need to look at the bias variance measurement or trade-off, right? Um, and this is something you can also incorporate when you are evaluating, maybe when you're doing that grid search or any of the search methods, random search or Bayesian, right? You can factor this in. So typically, how do you manage the bias variance challenge, right? Typically, what you do is um, if you have high bias, then increase model complexity, like I said, and reduce regularization if there was any regularization. We'll talk about regularization later on. If you have a high variance, that means the model is too complex. You add regularization or you simplify the model or you increase the data. Again, we'll talk about regularization when we get into neural networks. Simplify the model, like we said, reduce number of parameters, reduce the number of estimators, reduce the number of the depth of the decision tree, reduce the order of magnitude of a polynomial function if you're doing a polynomial regression and so on. Or alternatively, increase the amount of data that you're training that model with. Sometimes increase the number of features. Do more, increase the number of features if that is even possible. Get data that has more features, okay? But if you have a high bias and a high variance, then there's a problem. The problem is that somehow maybe your data is not properly represented. So you need to do a bit more feature engineering to extract features that the model can be able to see and depict. Now, the other interesting thing is the cross-validation that we just talked about can be very helpful in solving the bias variance trade-off problem, right? You can use cross-validation to detect variance, and we're going to look at how that happens. But the main thing is that if you are doing the k-fold, different folds in your cross-validation, you now find that the scores are jumping around a lot jumping around a lot for each fold that you train a model or for each instance, right? So that's how it detects variance. You have high fluctuation of fold scores. But how you can detect bias is all the folds will perform poorly in all cases, right? So that is how, and the reason why is the high fluctuation is because the model is, as is overfitting on some of the training data and not really overfitting on others. So that's how the values or the measurements. When we say the measurements or the scores, we are talking about the metrics again. We're talking about accuracy, recall, whichever one that you choose. So you can use cross-validation to do that. So the way you can tell after you do cross-validation, so take a look at this example. After doing 5-fold cross-validation on a particular model, right? How do you interpret this? You can see like this one. On the first fold, it has 0.91 score. Whatever that score is, whether it's accuracy or F1 or recall or precision. On the next one, it has 0.52, which is a very low score. On the third one, it has 0.88, which is high again. And the fourth one has 0.55, which is another low score. Now, fifth one, it has 0.93. So you see, its score is fluctuating. So when the score fluctuates like this, you know that this is a variance problem. It's a high variance. It is overfitting. So it's overfitting on some of the training data and it's not overfitting on others. So it's having a high score, right, on the ones it's not overfitting, and it's having a low score on the ones that is overfitting. Okay. So cross-validation is one of the best tools that you can use for diagnosing whether a model is having high bias, high variance, or whether it's a healthy balance. And this is very important for you to be able to tell because when you choose a model, you need to know whether that model is going to overfit on the data that you have or not. So for a case of high variance overfitting, your training accuracy will always be high, but the validation accuracy will be low. And then when you check the cross-validation scores, you see that it's inconsistent across the folds, like what we are seeing here. It's actually jumping around. Okay. And then if you check the gap between the train and validation metrics, for example, the training accuracy and the validation accuracy, you see that the gap is always large. So in this kind of situation, you know that the model is too complex and it's either memorizing noise or it's just too large for the data. So that's the first case. The second case is if you have a high bias. So high bias is where the model is too simple, is not adequate for the complexity of the data or the relationship between the data. So when you do that, you see that the training accuracy is low and the validation accuracy is also low. And the CV scores will be poor. So in this case, if all the CV scores were low, like 0.52, all the folds will be 0.52, 0.51, 0.3, low scores like that. Then you know that this is an underfitting problem. So when you do cross-validation, the scores would be consistently poor across all the folds. And if you check the gap between training and validation metric, it will be small. The difference between validation loss, for example, and training loss will be low, even though they are both not low enough, right? So in that case, you say your interpretation is simply that the model is too simple. You need to get a better model, um, you know, for your training or for your data. Then the third case is if you have well-balanced model that the model is good enough for the data, it's not overfitting and it's not underfitting, then your training accuracy will always be pretty high, right? Your validation accuracy will also be pretty high. They're almost close to the training accuracy. Difference won't be that much. Even when you have trained for a long time, right? Or you have trained different models, or even across multiple folds in cross-validation. And your cross-validation scores will be similar across all the folds. And they will be probably they'll be high as well. They won't be low. They'll be similar, but they'll also be high. And then if you check the gap between the train and validation scores, right, or metrics like the loss and so on, they will be small to moderate. So with this, you can say you have a good model. Okay. So this is how you should be able to interpret the results from cross-validation, the results from even during training the model and so on that will let you know what your model is suffering from. The reason why we're looking at this whole bias variance thing is so that you know what your model is suffering from. You need to know whether your model is suffering from a bias problem, in which case it is too simple and the data is far more than what the model is capable of, or whether it's suffering from a variance problem, in which case the model is too complex for the data, right? So after knowing what it is based on training accuracy, validation accuracy when you are training the model, or cross-validation scores when you do cross-validation, you can also now ask yourself, how do I solve it? Right? And you can see for overfitting, you add regularization, L1 regularization, L2 regularization, dropout regularization. We'll talk more about regularization later on. Then overfitting always means your model is too complex, is too big. The parameters are too many, are too large for the problem data set. So go for a lower complexity model. Reduce something in the model's parameter set or hyperparameter set, right? Reduce either whatever the number in the architecture rather. Reduce the number of layers if it's a neural network. Reduce the uh, reduce the number of trees if it is a random forest. Reduce the depth of the tree if it's decision tree, right? And so on and so forth. Or use a simple algorithm. Maybe just use a simple linear model. Use a simple linear model, maybe with a maybe one or two orders of polynomial transformation in your feature engineering. Okay. Or increase training data. Increase training data. Then use scaffold cross-validation for stable estimates. Use ensemble methods. If you're using a decision tree, use bagging, um, use random forest, use XGBoost, and so on. Okay. That is if you are overfitting. If you're underfitting, then if you have regularization, reduce the regularization. This only really comes in when you have a model that you know it is complex enough, is sufficient to handle the data, right? But it is still underfitting and you are using regularization, then reduce the regularization. But if you're using a model that is incapable, then use a model that is more capable, change the model algorithm, or increase the model capacity, add more features if it's available in the data set. If not, do feature engineering to add more features, right? Increase the depth of the trees, increase the number of estimators in random forest, and so on. Increase the order of polynomial in linear regression, and so on, right? Use more expressive models, models that have more capacity, like boosting, XGBoost, neural networks. Add nonlinear transformation, like I said, if it is a linear model, and add interaction features. Interaction features are basically new features that you create by combining other features. Then, if you have a situation where you have both overfitting and underfitting, then that's a very rare situation, right? Um, in that case, well, I don't know how you would have a high bias. Rather, you have high bias and you have high variance, right? Um, it just means that the model, so high bias and high variance, the way it would typically reveal itself would be that even as complex as the model is, right? Even as complex as the model is, it still is not able to predict your data very well. So you have a very complex model, it still cannot predict your data well. So the loss will be very poor. Okay, so let me see if I can depict that. So you have a model, something like this. The loss is very poor. The loss is very poor. I'll try any of these other ones. So the loss is very poor. So it doesn't go very low. The loss kind of hangs around somewhere. But the worst thing is that apart from having a high bias, because the loss does not go all the way down, it kind of stays very far away from having a zero loss, right? But you also have a situation where the validation loss is even worse than the training loss, right? And begins to diverge. So this is a case of kind of having both. So the first problem you need to address is, why is this loss even so low in the first place? Like, um, the model is not good enough, but it's also overfitting. So that's interesting, right? Maybe you need to re-engineer the features because it means the model is complex, but it's still not learning the relationships. So maybe you need to do some feature engineering. Maybe you need to improve on your pre-processing, right? Um, Parameter tuning and hyperparameter tuning, and then check your data quality. maybe you have a lot of outliers. Maybe there's a lot of noise in the data and your model is not able to learn. Because then if you're overfitting and your training loss is still not low enough, it definitely means that there is a lot of random noise that your model is not able to learn, right? So that's it. And I would have done a demo, but I think I've run out of time. So I'll instead do the demo when we come in next week before we jump into next week's topic. I'll take some time to look at that. So by the way, next week we will start with neural networks, and that is where the journey of machine learning begins to get exciting. So all what we have been doing so far has been classical machine learning, basic principles, and understanding all of the ideas around that. So from next week, we'll start looking at neural networks and what we can do with them. And then we'll go into some more advanced concepts. So I'll pause at this point. Are there any questions? Are there any questions? Okay. Um, so I hope this would be sufficient for you. Let me just give a sample of how you would do grid search. Maybe just um kind of review of it to help. I actually had something set up already, but because we've spent a lot of time on this, typically if you want to do grid search, let's just do a little bit of grid search. And when we talk about bias and variance, we'll talk about that um, when we do a bit of training. From next week, when we start doing more of the neural network stuff and so on. I'll just take maybe 2 or 3 minutes to show you. So first of all, we already have, um, so we already have, I'm going to share the notebooks today, but we already have, um, let's say we just wanted to do a little bit of some kind of, model search. I think I already have something I did where we tried different models. If you check the last class that we did on, I'll share the link, right? I did not use grid search. I just did a simple assessment of models using, and I think we can do that again here. I did a simple assessment of models using, I did a simple assessment of models using accuracy, right? I just use accuracy. But of course, you know that there are you now know that we can use, apart from accuracy, we can also use recall, we can use precision, we can use F1 score for classification, and then we can use MAE. MSE, RMSE, R squared, and a whole bunch of others. If you even go to sklearn's website, you will be able to see a whole lot of other different metrics. So if we even just import the metrics, um, sub package from sklearn, then um, we can get metrics recall score and so on. So we are going to do that. Then the second thing is just get the different kinds of models. So I'm going to look for a moderately complex problem from Kaggle that we can easily try out to see, right? Um, and we're not really going to do, we could manually train all the models. Let's try that. So let's start with a few. Um, let's say we just try, let me just try a few, maybe linear regression model, logistic rather, because it's a classification problem. So logistic regression, um, we try the decision random forest rather. Um, then SVM classifier. Then let's add well, let's just go with these three as an example. And I now want to so I have three models, right? A model with linear regression, model L. Sorry, logistic. I keep saying linear, but it's actually logistic. Okay. This ensemble. So we now have three models. Then we can basically train the three models and compare, right? So a simple way to do model search would have been to tick the three models, right? And then um, we will now run each of these models through a data set. And then I actually had done it before, so it is in model comparison. Let me find it. Uh, yeah. So um, you basically take and then yeah, in this other model I did a lot. Then you can train and evaluate. But yeah, the last time I did the evaluation with accuracy, I'm not going to use just accuracy. So for model in we can just have these three models, model L, model R, and model S. Okay. Um, we can then train. Okay. We train the model, we fit the model, um, we predict based on the tests, and then we well, there's classification report, right? But we could also do just metric dot accuracy and just put it in a results. So let's Say I have a results. Um, so I can then put this in a result. And we can just model equals model. And then we have accuracy score. We can also add the precision score, recall score, F1 score. Maybe you could even add the okay, R2 would be used for logic for regression problem, not classification. Of course, this I need data to make this work. So let me go get some data from Kaggle. Uh, so there are a lot of different data sets. I could just choose a spam email data. So the spam email data set, well, it has text and label. So this is a bit, I'll need to do embeddings and so. So let's look for something else. Okay, so a good example of what we could do here is, let's try, yeah, let's try the iris. Let's try the iris data set. So, but iris data set is not really complicated. It's linearly separable. So I think I want something that's more. We have mushroom. We have Titanic. So let's see. Okay, so we have training set and test set. I need to inspect the data. Um, this will require a bit of feature engineering, but let's see. Oh, okay. I need to sign in to have access to this. Look for something else. Okay, let's try this one. So this one is a malware data set where you have, this is a bit more complicated, but then it's a good way to test it. So you have a bunch of data that was generated from Microsoft, essentially malware. And the idea is we want to train models that can detect the kind of malware and classify it based on the data. So this one, we already have the data um, kind of cleaned. You have this first one, which is based on the assembly commands. So this is not feature engineered, but we have this other one that is feature engineered, right? And we have the tests and we even have the train. So for this one that is feature engineered, I'll use the values from the training and testing set, basically the same size. I use it to test. So let's get that. So to load any data from cargo, you need to import cargo hub. We can also import pandas. Okay. So once you do this, then we will need to um, download the data set, cargo hub dot data set download, and we specify the handle. Um, so we'll take the handle from here. You just take it um, from the URL. You can always copy it as well. You can also copy it from here. I think there's a place you can copy it from. But typically just take it from this URL and you download. When you download, take note of the path. When Kaggle downloads it, it returns the path where it actually saved it. Then you will load it with pandas and create a data frame from it. So you read CSV and it will be the data path, but you also need to know the sub path. The sub path, you can easily find it here. It is in this data explorer. So this data set is a top level. So for me to find it, I have to go into dataset train, large train.csv. So I'm just going to go in there, dataset, dataset, um, train, large train.csv. Okay. So let me double check that. Dataset, train. I'll use a test for maybe testing later. Train, large train.csv. So that's a data frame. If that works, then I should have a data frame that contains that information. Right. So we now have all of this, and there's a whole lot of additional data here. We could do a whole bunch of feature engineering here. Uh, but um, there's classification here. This is a class. There's a whole bunch of other stuff. So I'll just take these numbers and I will just do normalization. This might not be the right thing to do, right? Because um, yeah, but I'll just take these numbers and just do simple standardization on them, right? And throw it into my thing. So reading this data will take all of the it has 1,805 columns. So that's a lot of features. As a matter of fact, this number of features, if you put in a support vector machine, it's going to take a lot. So this data set is probably too large for me to use for this example. So let me go look for a smaller data set. Um, okay, so there's a mushroom data set which we can get from Kaggle as well. Uh, you can go to their data hub, go to data sets, and search for data sets here. So okay, so this is also not a plain data set. I'm looking for a plain data set that will allow, okay, let's go to enhanced breast cancer because I don't want to have to do feature engineering. Right. So this one works. Everything is already in numerical form, which is what I'm looking for. I don't want something that we have to do in feature engineering since we don't have enough time. So this is right. This is actually right. So we can just use this and we'll put in a data frame and we'll be able to see it. So again, you copy the handle from here. I'm going to go back and I'm going to replace the handle with this and download it again. Then here, I'm going to explore the data. So if you explore the data, you will again see the data explorer has just this, right? 1.73 megabytes breast cancer enhanced dataset.csv. So I can just copy that name. I'm hoping it should be there. Okay, going to copy that. It's not inside any folder, so I don't need to do a full folder. I just paste that here with the slash and we'll we should get it. So these are just numbers. I'm looking for what is just numbers. The only other thing is that the diagnosis here. So we'll do a little bit of feature engineering, but only on the actual label of the data, which we can do very simple um, data feature engineering. So first thing is we would just take the diagnosis out. It's either B or M. I think we've done this already, so shouldn't be hard. Um, so we get our X. Our X is DF. Um, yeah, well, I guess that's okay. That's okay. DF diagnosis. Um, so the Y, we need to turn this B into actual values. And the way to do that is We can apply a lambda to it. Trying to or we can apply a filter to it. Yeah, we could just do a very simple um equals to yeah, let's do it that way. Can use a map. I think that also works. So if it's M one, so one is a positive, that means malignant, B is benign. And that's it. So we get full get our full values of X and Y. We can print the X and Y. Let me just print just to see. Okay. Then we can extract. So let's extract the values. So I don't need to have the data frame. We'll get the values as numpy. Then we do test train split. So let's import, yeah, from model selection, we do the test train split. And we'll train and we'll just check it. So this is the first part where I want to do selection. Uh, and then we can now use the train and test and run this, which is what I was trying to do initially. So by the time this finishes the run, we can then make a data frame from it and print. So results data frame equals EF pandas dot data frame um, results. So this is going to give us a data frame of the performance of the three. SVC seems to have done badly. Precision is 0. Recall is 0. F1 is 0. Accuracy is very low. Logistic regression is also very poor. So this is a very good example of telling you which is your best model. We can already see that the uh, decision tree is much better, which is quite interesting. But then decision tree, random forest rather, yeah, the random forest is much better. You can see logistic regression didn't do that well because this is not a linearly separable problem. The simple breast cancer is actually linearly separable. That's what I used the last time I did something like this. The SVC is very poor, and its decision boundary precision is very poor, recall is very poor. I wonder why it's so poor. But I'm seeing SVC having okay zeros here. Yeah, it's having zeros. Uh, so something is going on here. 0.66, 1, 0.8. Well, it will have 1 for um zero label. but we have much better performance with a random forest classifier. So this is just where you could show how you use your model selection. I can tell you this is not the best. We could actually do better if we tune these models a bit. I just created these models um, without fine-tuning anything. So for example, the SVC, we could change the kernel. I don't know what kernel it is using, but it's entirely possible that um, I could change the kernel here. So just changing the kernel alone, well, the kernel is RBF by default, so should have done a good job. So that's how you do that. If you want to do grid search, then let's assume I want to do grid search on this random forest. So you would start by importing grid search from sklearn. Yeah, so import the grid search from sklearn. Then we can go ahead to do the grid search here. So let me just show how that can be done quickly. Now we want to maybe optimize the parameters, just the attributes, the number of estimators, and then for this, so going by the example we had, I'll add an extra 50, 100, 200, 500. Okay, and then max step. I'm not going to do this other one because it will Hmm. This will blow up the space. So here we have four parameters. So this is already 16, right? If I add this other one, 16 times 3, so we're going to have a larger grid search space. But that's okay. Probably going to be 16 times 9, which is 100, uh, 100, something, so it's so let's go ahead. Grid, let's do the grid search. Just an example of that. Grid search CV. And so we'll use a random forest classifier. Yes. We'll pass in the parameters, which is the parameter grid. And CV cross validation, we'll use 5 folds for the cross validation. So grid search CV is grids, not just ordinary grid search, but grid search with cross validation. There's also an ordinary grid search, I think. Um, okay, we don't have an ordinary grid search anymore. So grid search with cross validation. Um, then number of jobs -1 basically means um, select based on the approach, or based on the number of CPUs in the collab runtime. We use F1 here where we already had 0.995, which is a pretty high score anyway. So this is just for demo really. Then we run the fit, and after running the fit, it will take a while because it has to go through the um, total number that we are searching basically is 4 times 4 times 3 times 3, which is 16 times 9, which is 144, I believe. 144. Yeah. 154. 144. So it's going to search through 144 different permutations and combinations. This would be faster if we had a GPU. But as it is, it might take a long time. When this is done, then we can do print. We'll print the best parameters, and we print the we also print the best core. So when you print these two, this will show you um the best hyperparameters to use for this. But seeing as we already got 99, with the default parameters for a random forest, it's probably not going to be further than that. The default number of estimators is, I believe it's 200 or so, right? It's 100 rather. So, and the max depth, um, I don't know what that is, but the default number of estimators is 100, and we're getting already 99%. So, so that's it. That's just a quick look through on how you can do that. I'm saying this because that will be your next task. So if you are here, that means you already have a head start. All right, that's it from me. Uh, so let's have a good evening. See you next week. Good night. I'll share this later on once it is done so you can look through it.